Okay, so there are certain similarities between the two, and then there are certain differences between the two. Let me briefly, very quickly go over them. And for people who are taking quantum mechanics next time, or people who have done it already know about this, but people taking quantum mechanics next semester, you will be doing a lot of this next time. And for those of you who have seen it before, woohoo! Okay, so in both types, classical and quantum, we express a complete state of the system as a function of time. Which means all we care about, well, not all, but mostly what we are concerned about is how does our system evolve over time? If I have a car moving at a speed 55 miles per hour, where will it be in, say, 30 minutes or in 60 minutes or however long I have? In both types of quantum mechanics and classical mechanics, we want to know the state of our system as a function of time. However, there is difference. So the difference is that in classical mechanics, a complete state can be treated as if it was located at the center of mass. So do you guys, so people who have taken Newtonian, do you guys remember when we did the system of particles? We talked about that if there were many, many bees and they were all flying together, how do we do the evolution? Do we keep track of every single bee in our system, which will be really, really difficult? Or we can just do a collection of bees, figure out where their center of mass is, and follow the center of mass as it goes forward. Do you guys remember that?
Yes.
Those bee concepts, right? We remember that. Okay. Whereas in quantum mechanics, a complete state is just a pure quantum state vector. Now, I've used this word quantum state vector. Now, what is a quantum state vector? A quantum state vector is just an experimental procedure that can be used to prepare or test one or more physical systems. It's not actually a state property of the material. Okay, just know that. Even though, I mean, we're not going to deal with it until you guys get to quantum mechanics, but you should know what it is. I can't hear. Can someone say yes or no?
Yes. Yeah.
For those of you who are going to be taking it next semester, you'll know that very soon. So it is not a physical property of a system, but rather an experimental procedure. Depends on the system, what kind of a procedure that would be. Number 2. So similarities is that for both classical and quantum, so for both classical and quantum mechanics, we can write an equation of motion that expresses the complete state as it moves forward in time. Okay, so then what's the difference? What's the equation that expresses it in classical mechanics?
In the book, Dr. Zane. You should read it.
Well, you should know that one without reading the book.
Well, is it not in the book?
It's that one, right? What is it called?
Called the Newton equation.
Yep, that's it. It's the Newton's law, right? Newton's force
Yeah,
equation.
definitely what I said.
And in quantum mechanics, what is that equation? So this was Newton's law, Newton's force equation. Anyone remember what that equation was in quantum mechanics? And what was it called? Or to make it more scary, I could do the other one.
Yeah, write the other one.
Please
don't.
Write
Write
the
the other
scary
one.
one.
Yeah. No.
The time-dependent one. So the time-dependent Schrödinger's equation and time-independent Schrödinger's equation.